happens that in the next minute or so, that you just go ahead and begin your presentation with your normal pace that you're expecting, of it being 20, 25 minutes. And hopefully the dean will be able to join halfway and then join the discussion. But I think it isn't worth us all waiting until at least 2:20. Julie, do you agree with that? Or
yeah, I emailed her a reminder, but yeah,
okay.
I think it's fine to begin whenever Ben feels ready.
Okay, sounds good.
Yeah, and maybe as you're setting up, and I'll just mention to everyone, this is a Thesis B presentation. This has been final semester and his final work. So the conversation here is typically a bit more about, it's not about next steps for the thesis necessarily, but next steps in Ben's career and moving on from here. And so all criticism or all feedback is welcome, but just keeping in mind where this is within the sequence. We do have 2 Thesis B presentations, one following Ben's, and then we'll have 2 Thesis A presentations at the research phase a little bit later in the afternoon. So that being said, I'll let you take the floor, Ben.
Awesome.
Dan, hope you're doing well. Good to see you.
It's good to see you too, Professor Garrison. Thank you. Well, so welcome to my thesis presentation. I've Ben Marshall, if my name didn't give it away on the sheet and on my face here on Zoom. My advisors for this, my supervisor was Professor Faulkner, and Michelle Addington was Dean Addington was my co-supervisor. Professor Nagy from the engineering department was one of my readers on this one. So as a kind of part engineer, part architect, I like to start with a problem, like what's, especially for a thesis that I'm trying to design something to solve a problem. So what is the problem? That is, of course, sweating, thermal comfort. Humidity is kind of what I'm going after. The reason why we sweat is our bodies are trying to use evaporation of that sweat to cool us down. But because of relative humidity, sometimes that doesn't happen. This is just a real quick representation of relative humidity. Both cups have the same amount of water in them. However, one cup can't hold any more water, while the larger one can still hold some water. And that's where, if you've got evaporation off your skin, if there's not any more holding capacity in the air for water, it has to do with vapor pressure. It's a little bit more complicated, but this is kind of the main idea, is that there's not enough room in the air for some more water, which is why we get uncomfortable. So this is a psychrometric chart. Psychrometrics is the study of water and temperature and how they kind of mix, the air and temperature. And so the red bars show the ASHRAE comfort temperature, one of them that changes every couple of years. But this is one that I grabbed, 68 degrees on the low end and then 82 degrees on the high end. But above, on the vertical axis, is your humidity. Above 0.012 kilograms of water vapor in the air per kilogram of air, things start to feel a little wet. And that above that line in the graph, things start to feel a little wet. And that's something that I have experienced living in Florida and growing up there, and something that I kind of wanted to address in my project. Another problem with humidity not only is your thermal comfort, but also high humid environments mold loves to grow in high humid environments, which is not only bad for your building, but also bad for your personal health. Even if it doesn't grow mold, high humidity can degrade building materials like plaster and gypsum board and that sort of thing. So we as in the human race, have already got a way to deal with humidity. We've already got technologies to deal with that. The most kind of common one is vapor compression, where we have a cooling coil and we run really cold coolant through there, and then we compress it and make it really, really warm to reject the heat to the environment. But when you get that cooling coil really cold, below the dew point temperature, you get condensation, which pulls the water out of the air and dehumidifies the air before it is put back into your room or your building. So we also have other ways to dehumidify the air with desiccants, either solid desiccants with a wheel or liquid desiccants with some kind of mixture of chemicals and water. It's a salt is sometimes used, lithium chrome is used, a couple others. But this is a psychrometric chart showing the outside air is the big red dot, and what we're trying to get to is the room air, which is on the bottom, the purple circle. On the left in the blue is how vapor compression works. It cools it down and then reheats it. On the right is how desiccant systems work, and it's a lot more complicated. The reason why it's more complicated is because desiccants need to be dried. And so that's why there's all these zigzagging things going on there. But if you look at the length of the two blue arrows, that shows roundabout the same, the amount of energy you're using for cooling for both of those. So desiccants use less cooling, but they're a lot more complicated to work, at least in the current form. So why do this whole dehumidification without cooling? It seems like the cooling is a lot more simple. Well, if you can use less energy, there's a couple of different times when it's really helpful, such as radiative cooling. When you don't treat the air in the space, you radiate heat from your body, and these panels soak it up. So it is a lot more efficient than doing air cooling. Also, anisotropic wall assemblies are similar to radiative cooling. They kind of soak up the heat into the walls, and the heat is pumped away to a different spot to be rejected to the environment. Another time when this would be very helpful for energy efficiency is in cooling in shoulder season hours, or sometimes called pre-cooling, where the air outside might be within your ASHRAE comfort temperature bounds. It's somewhere between that 68 and 82, but the humidity is just way too high. It's too sticky. Usually you turn on a vapor compression system, use a lot of energy to cool it all down, but that's a lot less efficient than just soaking up that humidity. So is there a way that we can do this instead of having all that soaking up and drying out and adding heat and all that sort of stuff, to do dehumidification more simply? Well, biomimicry is kind of the study of nature, the way that nature has solved problems in order to apply those problems to current day, or apply those solutions to current day problems, excuse me. The lotus leaf is a plant that has these little bumps on it called trichomes, and they're covered in a little bit of waxy substance that doesn't absorb water. And because of the shape of those bumps, the surface tension of the water will keep it beaded up into little droplets rather than soaking into the leaf. Another plant that has these same trichome-like bumps on them, you've probably seen around here, or if you go down to Houston or New Orleans, is Spanish moss. And we have ball moss and things like that. The bromeliad family has got these trichomes. It absorbs water from the air because it increases the surface area of their leaves, basically, of their tendrils, and it has some water absorbing chemicals on it. So my question was, could we do this artificially? Can we make this so that we can dehumidify our buildings somehow? I think we can. I think it needs some more work, but this thesis is the first kind of step on the way. This is a mesh, copper mesh that was created by some researchers, material scientists out of the University of British Columbia. It has got similar kind of trichome looking things on it, and these are grown copper crystals, copper oxide 1, and then a little cap of copper oxide 2 on top of it. The copper oxide 2 doesn't like to absorb water very readily, and because of that, it kind of creates a hydrophobic, which just means that water beads up surface on top of that. However, if you run a current across it, as you can see on the right, in the water removing mode, get rid of that, it will oxidize, and that means that you'll get some water absorption. You'll strip an oxygen off of that copper oxide. It'll become a copper 2 oxide, and then it will bond to water, strip a a hydrogen away from water and create hydroxide, kind of the stuff you pull on your knee when you skin it up as a kid. That process it allows this thing to soak up water. And if you add more electricity, that copper 2 oxide end up becoming just straight copper, and you get some more hydroxide. The researchers also found that depending on if you gave it a frequency of an AC current, you could get it to switch between superhydrophobic, so rejecting water, and superhydrophilic, like accepting water. And so that was very interesting to me. I thought that maybe instead of having to dry meshes that soak up water, we could get it to bead up water like a lotus leaf and drain it via gravity, which would use a lot less energy. So I decided to make some of this, and I made it this past fall with a grant from the University of Texas at Austin's School of Architecture's Materials Library. And I had to bone up on my chemistry to figure out what was going on and to make this slurry, this electrolyte solution. So this blue stuff, it looks kind of like Kool-Aid. It's not. You shouldn't drink it, but it's got a bunch of copper and sulfate ions in there. And when you run a current through it, you put some cathode and anode, you create an electric current through it. It will grow crystals on that mesh. That is, and if you turn the dial just right on your current, your voltage, you'll get different kinds of crystals, which is what the cookbook from the Kung et al., the folks from British Columbia, kind of laid out in their paper. So this is my first run at it. You can see that there's a couple of different colors to this mesh, these mesh pieces. I've got 2 different mesh sizes, and then the mesh, I guess, woven sizes. And then, of course, I did a couple of different physical sizes as well. But you can tell that some of them have different amounts of coating because I cooked them for a little bit longer in that solution. So after I figured out how I wanted to test this, I did a second run, the B run of meshes, and then the B1 through 7, and then the last letter, A or B, is the size of the mesh. One is kind of like a bed sheet woven thickness or kind of density, and the other one looks kind of like expanded metal. Here are the final samples that I used. The A meshes are on the bottom, the B meshes are on top. So now that I had those this spring, it was all testing. So I created this testing loop, which is kind of like a squished oval out of PVC, 4-inch wide, 4-inch diameter PVC. I put an inline fan in there, and I put a little opening so that I could insert some humidity through a humidifier. And I have an inlet and an outlet for the testing machine, which is shown here on the right. So Lycor 7000, that it'll pull a sample out, it'll test the CO2 and H2O, and then it'll put the sample back in so that I'm not losing any air or not losing any of the sample, so that I can tell if it's soaking up water or not. And in the center there is where I'm putting the sample in a little blast gate valve, and I'm hooking it up to some electricity to see if maybe my original hypothesis that we can get it to drain would work. So this is that blast gate valve. It's something you'd find in like an architecture shop everywhere. It's just the same thing you would use to open or close a table saw to suction, so that you can suck away dust particles and that sort of thing. I pulled the plate out of the center of that, and then my cousin who lives around here in town is 3D printed another plate for me to insert my samples into. And you see some copper buses right there. That was an idea from Professor Novotselak about making sure that I had the electrical charge on this thing evenly distributed. So that is what that testing sample looks like. It's over in the Pickle Research Campus right now. And I've got I sealed it all up with rubber cement compound, which is waterproof. And then I taped on top of the joints to make sure I got it sealed, which is important. I'll get to that later because I didn't have it sealed. I did some work with the fan to make sure that I could get some laminar flow or turbulent flow through the mesh screen, because if I can get some turbulent flow, I'll get more of the water vapor hitting the screen rather than some that might bypass through if it's just going straight. And these are those tests that I used a pressure meter to figure out. The Lycor also has its own little pump to pull a sample out of the chamber, and that becomes pretty important later. It has, when the pump pulls it out and puts it back in, it ends up with a air velocity of 0.002 meters per second. I also did some quick pressure tests to see what the pressure drop across these mesh samples would be, because you put them inside a duct, kind of like a filter, or maybe in a window as a screen once I get them working. So what did I get? Well, I got leaks. And I also tested the fan speed, the mesh size, the mesh construction, or how long I baked each piece for, the active absorption with electrical input, and passive absorption, which I was not expecting. So to figure this out, because I had a leak, I had to use some equations that I got from my indoor air quality class here at UT. The lambda equation number 2 is the kind of derivation of the first one. The lambda at the end is the air change rate. If you've done a lot of indoor air quality stuff, or if you've understand some HVAC stuff, air change rate is how many times you change the air in a space per hour. When you multiply it by time, that's basically what percentage of the air in your space has been changed out at whatever time you multiplied by. So leaks, lots of leaks. When I first started, this graph here on the left shows the water concentration. I wasn't using any kind of filter or anything. It was just a closed loop without any of my samples in there. And you can see that within 0.35 hours, I changed out all of the air in there. I had a big leak somewhere. And the little equation up on the top right of each of the graphs shows y equals something times x. That something is the air change rate. So I was changing out 2.7 times 2.7 of my air per hour, which is way too high, because I figured that the amount of water that I was going to capture in the stream was very, very low. So I needed the leak to be very low, or else I wasn't going to be able to see it. So I did a lot of taping, and with multiple different kinds of tape. And so I got the air change rate way down to 0.08, basically. So 0.08 of the air is changed out every hour. So very, very low, which was helpful later on. I also mentioned that I had a inline fan in here. I tested out a couple different speeds. At the higher speeds, I was getting a lot of noise in there, probably because of that turbulent flow. I'd also, because of the pressure difference between the inside and outside with the fan going at high, the leak was worse, or at least the difference between the CO2, which is kind of my tracer gas, it's not going to bond anything, and the water, the difference between those two is very low here for the high fan. Low fan, you see that it's starting to separate. So the high fan, I'll go back to that, the difference between them was 0.0 something, so 0.05, I think, between these two. But if I go to the low fan, you can see the difference was 0.25. So much bigger difference because the leak was much less. And if I go to using just the Lycor pump, the difference was astronomically different, very, very big. So the leak was very small. The CO2 kind of shows how much I'm leaking, and the water air change rate shows how much water I'm losing per hour to the mesh sample that I had in there. So this stuff is doing some dehumidification. So trying to figure out my different mesh densities. Mesh A was the real dense mesh, kind of like a bed sheet, almost very, very densely woven, tightly woven. And I figured that this would have more surface area than the kind of expanded metal copper mesh. And so I would get more dehumidification. But I was very surprised that I did not. This is mesh B. I got in the same amount of time, both of these graphs are 0.26 hours, 0.25, 0.26 hours. And in the same amount of time, I got way less. Well, not way less, 0.14 parts of the air changed compared to 0.2. So yeah, definitely more more water absorbed with the B mesh, which was interesting to me. Another thing that was interesting was that I thought, hey, same thing with the mesh densities, that the more I coated them, the better they would do, right? Well, evidently not. There is a sweet spot, it looks like, because this one, the B5, 6, and 7 were the lowest performers. Actually, B4, 5, 6, and 7 were the lowest performers. And then when you got up into the top 3, B1, 2, and 3, they performed better. So I'll get into a little bit why I think that happened at the end. But I thought that was a very interesting find. Mesh B was a little bit different. I still had the top performers were still B2, 3, and 4. So there seems to be a little bit of a sweet spot for that, but this seemed to be a little bit less affected by the time I cooked it compared to that first one. So I wanted to check and make sure that I was getting, that I wasn't seeing things. So this is a comparison between the average absorption rates and of these two different types of meshes, the A and B mesh, compared to an uncoated sample of theirs. So the yellow, of course, goes with the just a second. Yeah, the gray goes with the blue and the yellow goes with the red. And so you can see there's a definite spread between those two. So I am getting a higher loss rate of water with the meshes that are coated than I am with the meshes that are not. And part of this is also that I have leaks still. And so I'm going to lose water no matter what. It's just at what rate I'm losing the water. So the part that I was really interested in doing was getting rid of the complicated bit of desiccant dehumidification, which is where you have to reheat the desiccant to get rid of the water. You have to bake the water out, basically. And so I wanted to figure out if there's a way I could drain it by using electricity to absorb water, more water, or desorb water, depending on which charge I put on the mesh. It looks like at this scale, I'm not seeing much of a change when I electrify it. And I thought for this one that maybe it was just a time thing. So this one I did for a full hour, and I was not seeing any difference, but maybe it's that there was just too much noise in that water sample, and that if I got it to where there was basically no noise, that I would see a little dip when I turned on the electricity. So I ran one for 7.25 hours, and I didn't see any change in the slope of my water loss for this one. So it looks like at this scale, not really a. It looks like my hypothesis was wrong, but this is with using DC power, not AC power. So I'll get into that in a second. So this is active absorption, where I was trying to do something using that same test. I ran some other numbers. You can tell that there is that the CO2 air change rate, the loss of CO2 is very, very small, very low, very small leak, but the loss of water is decent. I am losing some water in this sample. So I am absorbing water somewhere, and the only place I can absorb water in a PVC pipe that is waterproof is my mesh sample. So having that passive absorption, I wanted to find out how much of the passive absorption I was getting. So this is the output from the Liquor about concentration and how long I've run it. You can see a little dip at the end. That's when I pulled the sample out and outside air started coming in. So that's not part of the test. But you can see that on the left, the water concentration is in millimoles per mole. And I started at about 19 and I got to about 13.75 over the course of 7 hours. And so doing a little bit of math, we find out, and using the number of moles of air in the device, we find out the change in absolute humidity is 0.00345, which is not nothing. If you take a look at the psychrometric chart, and I'm at 25 degrees C for this loop, I went from 60% relative humidity down to about 45% relative humidity. It did take 7 hours, so it's not a very fast or powerful process, but there is some passive dehumidification going on in there for some reason. And so this is what I think is going on. In the mesh from Kung et al., we've got the coating of copper oxide 2 on the outside, which is this darker brown on there. And it doesn't really react with water as readily as copper oxide 1, which is the lighter stuff underneath it. But it doesn't have to when you're dealing with liquid water. Liquid water beads up because of the surface tension of water on top of this mesh. And so the water never gets down to that copper oxide 1 to be absorbed. But vapor water doesn't have surface tension at all. So it just flowed in and out of all the crevices of that mesh and was able to get down below the copper oxide 2 coating and start to be absorbed by that. And which also, this is all hypothesis, but this would also explain why the more coated, the samples that I cooked longer don't absorb water as fast or as much as the samples that were cooked less, because the samples that were cooked longer have more of that outside coating on them. So some stuff I think, if I were to continue this, or if someone wanted to pick it up and run with it, some future testing suggestions would be to increase the surface area of the meshes to increase the amount of water that you could soak up. So stack them up into a kind of a multi-pass test. I would also want to do AC instead of DC. I use DC because I just wanted to prove that it worked. Something happened when I turned on the electricity. So I didn't really use AC power, which is what the researchers from British Columbia did. So I'd love to test it out with AC power now that I know that something is happening. Another thing is to test higher humidity. One of the things in the literature review that I found on desiccants is that they work different depending on the relative humidity around them. So higher the humidity, the more they can soak up. The lower the humidity, the closer to kind of equilibrium they get, and it's harder to soak up water. I'd also like to compare the absorptions between all the different meshes. Because it takes so long, or it took so long, that 7-hour test, I would love to sit down for a whole summer and just test it in my off time or something and figure out what the different absorption rates and amounts are for each of those meshes. So that's what I've got. That's my thesis in a nutshell.
Great work,
Thank you,
Ben.
Ben.
Thank you.
Yeah, thanks, Ben. We'll open the floor to questions and comments.
Ben, I have to give your advisors a lot of credit in terms of helping you really focus and really produce something that's really, I think, quite important. Since I'm going to talk first because I know they know more than I do, and so they've been telling you all along. So I'm from out of the blue here. I have done a little bit of looking into the idea of capturing and condensate, and I am familiar with some of the research out there. My question to you is one is a question, and then the second one would be a suggestion. The first one is that I'm familiar with some other research in which they're looking at other materials besides the ones that you chose. Looking at some researchers that are using hemp and in a fabric. So they're actually weaving a new kind of fabric, but that's not what's important. What's important is that the way they were getting the moisture, which they were collecting at night when the humidity level was above 70%, in this mesh. What was important out of it is the way they used to get the water out of the mesh, which is they used heat instead of electricity. And so my question would be, have you looked at the idea of using heat? Because in the daytime, especially in the Austin area, we have relatively low humidity when it's very hot, but we do have an excess of heat. So maybe heat, it might be something you need to think about in terms of driving that flywheel. My second point, which is a recommendation, a thesis student that I've been working with in the BDS program this semester, we just got a paper accepted at the nanotechnology conference. And I guess what I'm asking is, are you at that level to be able to sort of write an abstract for getting your work in at least a poster or a conference format? I think the nanotechnology, the International Nanotechnology Conference would be a great one. The reason I'm mentioning this is I think the deadline for the abstract is like today. So, you know, not to put any more work on you, but I think it's, you know, our paper was accepted. It's not, we're doing something on memory alloys, but I think your work, I think, is certainly of the stature that could be there. And I'd like to see it get reviewed by a wider audience. And so if you want some information about it, I'd be glad to talk to you about it. But I think that what I've seen here is really first-class research work.
Thank you. Thank you. I appreciate it. Please send on that information about that abstract. I've got one due at the end of the week for another conference, but I think the nanotechnology would fit my thesis a little bit better than the other one that I'm working on. So the heat is definitely used a lot for dehumidification or for desorption of desiccants, and a lot of the research that I have seen not only uses like process heat from other machinery in maybe a factory or a facilities place like University of Texas has got a facilities.
Or solar heat.
Or solar. And solar is one I've seen in Europe used a couple of times. I haven't seen any examples here in the US, but that could be used as well. The reason why I was using electricity was not to heat it, but to see if I could get the electricity to bead up that water on it and let it be drained away via gravity, which I suspected was going to be a little bit more energy efficient than using heat. But at this point, it doesn't do that. So maybe it'll work with heat where it wouldn't have worked with electricity. Thank you.
I'll jump in there, Ben. I agree. This is really cool, and I'm very excited about what you've come up with here. I've got two questions that I'll pose. One I think I might have asked you at the end of your first semester of this, and I'm wondering if you have any new thoughts in this regard. And the second is just about the process a little bit. The first one was, do you feel like the blowing the air through this mesh is essential to make this work? Or could this kind of this oxide be applied to other, say, wall finish surfaces or other surfaces in a building, because that would open up a lot of possibilities for the kind of surface area you create without having to have, a special structure. It could actually, maybe there's the potential that this could actually become, part of the interior finish of the building. I don't know how you drain the water off of it, or, that whole, side of the equation, but it struck me that those samples you produced are quite beautiful, in addition to having a function, and it seems like it might require quite a large surface area of them to get the dehumidification performance that you need. So that was one question. The second was, do you have any sense from your testing of to what extent you may be condensing moisture on the trichomes into droplets that are then getting re-evaporated back into the airstream? And if that is a substantial effect, have you thought about any ways to maybe put this on a belt where it's sort of like a, some ERVs, the desiccant wheel sort of turns periodically so it can absorb and then desorb out of the main airstream? So those were the two questions I had.
Yeah. Well, on the building materials side, I think it might work. The problem is that you've got to get your material submerged in this electrolyte solution and then run a current through it and that sort of thing. So you'd have to have a pretty big facility, I guess, or at least a long tank that you can run not boards, but some kind of metal through that you can deposit these dendrites on. It could, yeah, I'm not sure. I think the reason why the researchers did it with copper was not only because of the similarity of the metals to the dendrites, but also because of the real good conductivity of copper to electricity, which is kind of what they were studying, the use of electrical current to turn it on and off between between super hydrophobic and super hydrophilic. So I don't know. That would be an interesting thing to put it on a panel. The stuff can rub off. You can rub it off with your fingers. And I actually did some of that at the end because I kind of scraped away where the dendrites were on the outside so that I could make better contact with it with the electrical inputs. So it'll get all of your clothes if you rubbed up against the wall, but that would be interesting to figure out how I could implement it into architecture. The second one, I think I was seeing some, you saw in my fan speed test that the high speed fan, there's a lot of noise in there. And I think part of that was that it was absorbing some and also getting desorbed back into the air as the high speed of the air coming through there stripped those water molecules back off for sure. So I don't know. It requires more testing to find out whether or not I can isolate that though. Figure out how much I'm losing.
Hey Ben, I have a couple of comments. One is first, I really enjoyed your presentation. I really enjoyed it. I thought it was I think it's a good example of sort of having a research question, then having a method like an experimental method to test this question. And then through the whole process, you're discovering things that you did not expect, right? And you're learning through that process. And then you're getting final results, which you're sharing. I think that is something that's really important for us as designers, as practitioners. Is just, maybe even more important than the results that we get is really the method that we learn to implement, right? As how do we approach a problem in life and any type of issues. From my experience, one of the things that I feel, and it's more something, I guess, of a self-criticism of myself and my work, and then sort of trying to give you some suggestion is, I feel that it's always important to share like the final result in some form that is, let's say, usable by a practicing designer or engineer. So I was wondering if there's a way to, I thought that what you showed in the beginning with the psychrometric chart was very clear. It's something that we all use. Could we have something that connects at the end, let's say, the performance of a system like this as how it reduces relative humidity in a certain volume as connected to air change rates in that space and maybe energy use. So we can actually see how much, how much of this stuff do we need in a certain space if it's this size and if the relative humidity is X, Y, or Z, something like that.
Yeah, that's a good suggestion. I've been struggling over the past couple of days to figure out how to apply it, because I really do like applying whatever problem solving solution that I've got. I guess the closest to that was showing the relative humidity change within the chamber at the end there, but I think that it would be better for sure. I agree that it would be better if I could figure out a way to, or a metric for how much volume you need of this stuff to dehumidify a standard room, maybe. Yeah, I'll be working on that. Maybe for the paper that Professor Garrison was mentioning.
I noticed that Zoltan had his hand up at one point. And Ben, maybe if you stop, since we're having just a general discussion here, we can just
Sure.
a little bit better, perhaps, unless someone wants to refer to something specifically. But Zoltan, did you have a specific comment?
Yeah, and a lot of smart people went ahead and made all the smart comments I wanted to make too. But I will congratulate Ben for your work and the, let's see, how do you put it, the dedication and the persistence, and then the use of all the duct tape and making sure it really works at the end of the day, right? I mean, it's not obvious. Sometimes you give up halfway through and do something else that's easier, maybe some simulations, but sticking through the experimental work and then doing all the runs is commendable. So congratulations. I wanted to throw in another possibility to study down the road, and it's sort of like at the complete opposite end of what Dason said. So you get the full bandwidth, which is if you could build a device that's the size of a filter for the home HVAC system, and you could slot it into the air handler. You have a fan in there, and you basically can dehumidify for free. There's also electronic basically there. And all you need is the size of the, whatever the $10 filters that you can buy in Home Depot. And so that would let you dehumidify within the existing system without running the cooling, but just running the fan. For those days, as Michael said, where you don't necessarily need to cool down to dehumidify, like the last week or so, where it was like, 75 degrees, but 70% humidity, and you're just sweating. But you can choose between sweating or freezing, but there's nothing in between. And so I think, if you can scale the technology in a reasonable way, or somehow you make it plug it in there, or at the exit, at the vents where the air gets into the rooms, then you have really the highest impact. Because afterwards, all you do is trying to locally remove the air, like on a wall somewhere. And that's, then you're starting to talk about diffusion of the air there to make it work, or you have to add a fan to pull it around. So if you're going to make an impact, especially in residential buildings, you need to put it where the air is flowing already. And you've laid the groundwork. I mean, you literally built that system. You just need to scale it out. So anyway, that's my 2 cents. Congratulations, and hope to see more from this. And I agree with all the people saying you should write papers. That's good.
Next step.
Oh, go ahead.
Yeah.
Michelle.
Also, that is a better idea. Good call.
Hi, Ben. First of all, sorry I wasn't part of this sooner. I think I'm not part of the regular invite list, so the only way I knew about it was that my name showed up on the schedule that we were all sent. And so that's why I was going with the 2:30 time that was on the schedule. But I did read this. I did get a copy of this last week to read this, so I'll be able to deal with my comments from that. So hopefully that reflects what you talked about today was what I was reading. I think the part for me that was a little difficult to follow was this kind of switching back and forth between liquid water and vapor. They're two radically different animals here. And so if you think about hydrophilic and hydrophobic surfaces for water, they are for liquid water. They're all, and they operate according to surface tension. So you use the system for surface tension. And so I got very confused in this in terms of, were you sort of using it in a way that, it was actually meant to be combined with condensation to remove liquid water out? Or were you actually thinking that the same principles that dealt with liquid water would deal with vapor?
So my assumptions with this were that I would get vapor because it's a chemical process, electrochemical process, that I would get vapor absorption by the mesh screen. But my hope was that I could reverse that. Once I've absorbed to a certain capacity, I could reverse that and then form liquid water that could be drained away. Because the big, actually, we weren't here for that part because we started early. One of the big problems with current desiccant dehumidification technology is you have to dry the desiccant.
Yeah,
with heat
I know
afterwards.
desiccants quite well. Yeah, so
Sure. And so I was hoping that there was a way that I could use desiccant technology. I could use this to, instead of drying it, to drain it. And so I wanted to absorb a critical amount of vapor water and then switch the mesh to desorb it into liquid water because it was attached to that screen. And because of the geometry of those trichomes, the dendrites on there, I could drain it away kind of like floater sleep.
it's a lot of different physical processes. And I think what would have been really valuable in this is this, if you'd actually sort of walked through completely what the different physical processes were, what the different chemical processes, what was the actual sort of mechanism for absorption versus sort of dealing with surface tension, sort of, and even walking us through the equations for this to sort of understand why this material, why this quantity of this material. But I kind of got the feeling for this is that you were hoping, you were hoping that you would get all of these different processes collected on this material that's actually meant to do something completely different really, that all these things would happen, and that if you just kept sort of experimenting with different ways, you'd get something from that. Not to say that this experimentation wasn't terrific, because I think that what I would want for a master's thesis is someone to define a framework, a question, and a process such that the really important questions emerged from it. For a PhD, then I'd want you to pick one of those questions and focus in. But for the master's, I want you to sort of find a way so that in the same way that we would do a field study to collect different kinds of information, or a case study to sort of reveal certain salient characteristics, that you have the right framework to get all those. And I think those come out of it, but I'm not seeing it in the right. I'm seeing lots of things about how the experiment leaked. Those are not things that need to be in a paper that you publish on this. But what will need to be in the paper that you publish in this would be a clear walking through of the different scientific, of the different phenomenological and physical reactions that are taking place. And also thinking about it from orders of magnitude, like which of those reactions is the driver, is the important one within it. When does differential partial vapor pressure supersede the chemical absorption, which I'm a mechanical engineer, so I don't know as much about chemical absorption as I know about how we would manage vapor pressure or surface tension. So when do those come into play, and which one really matters on that? You may not be able to determine that from this, but if you could sort of lay out, and I'd love to see that walkthroughs, and probably less of the many tests of this. And the same thing is true for thinking about when you put a current on that. The current can do and cannot do many different things. It can produce the differential heating that will give you a vapor pressure differential. And that vapor pressure differential could allow that membrane to, concentrate more of the water vapor. But if you're sort of like have high airflow across it, no, that won't happen at all. It'll have to be laminar flow, on that barrier to take place. It could, and again, we move into electrical property area, which is definitely not my area. It can have something to do with ionization. Now I'm making stuff up because I really don't know that part of it. But it also has thermophoretic characteristics as well that could come into play, which means you heat up something else in order to drive it in a particular direction. So there's lots of things that can emerge from this. And I would encourage you for this next level to actually sort of let go of trying to make the device. You use this and use this mechanism, to explore and find out more about it. Let go of that and sort of like follow what the really difficult or really interesting question that emerges from it, or the one that has the most potential, and see where that takes you. And I don't necessarily think it's going to take you to a filter that you put into an HVAC system. It might arrive someplace else, but until you actually sort of walk through the full science of it, don't run too fast ahead of it. Because what you've demonstrated is you have like a remarkable ability to actually sort of engage, test, work at this kind of level. We have confidence that you're going to be able to make whatever you're going to need to make from it. Don't make it too soon.
Thank you. I appreciate that.
Those are great comments across the board, really, Ben. And I think your work has merited this discussion. I don't have much to add to this other than to just mention that one way to think about this, as I often try to think about a way to jump scales and allow something to be applicable to different modes or different aspects of architecture and or engineering. And it gets me thinking that perhaps one of the bigger questions that you're asking or questioning is really an optimization of surface, which is something that could be thought about in many different ways. And of course, as it relates to state change, humidity versus time, but one could imagine how that could scale up to a lot of the built environment to think about optimization of surface or mass or density, filtration, those types of things that that transcend the very specific exercises that experiments that you were doing, that at least for me becomes inspirational to start to kick off other modes and means. So I congratulate you on finishing the work. I don't know if anyone else has any other concluding comment, but and I think everyone had, I think all the reviewers made comments. So just, congratulations, Ben, and to you and your thesis committee. Thanks to the advisors as well. And that's what I have.
And congratulations on getting into the PhD program. Yes. I really look forward to seeing how you develop in that. Have high hopes for you.
Thanks. Maybe I'll be able to ask more achievable questions.
I'm no. Don't worry about the achievable questions. Worry about the questions that really break new ground. Yeah. You have a long time to work on a PhD.
I hope not that long.
All right, so thanks. So thank you, Ben, and Maite, you're next. When you're ready, you can share screen and kick off. Again, just a reminder, we have 2 Thesis B presentations that we're kicking off with, and then a slight gap, and then the Thesis A presentations to bridge the 12 time zones that we're covering today, which has partly to do with the discrepancy of the scheduling today and the challenge of trying to make this all work. But thank you all for bearing with us. So Maite, go ahead.
Well, hi everyone, and thank you so much for being here. So my thesis advisors with Dr. Faulkner and Dr. Lieberknecht I'm evaluating the cooling potentials of vertical greenery systems in urban residential areas to mitigate urban heat island, reduce energy loads, and improve thermal comfort conditions in a hot, humid climate. So in this presentation, I'm going to go over rather rapidly over the problem, the proposed mitigation strategy, and the case study site I've selected, go more into depth into the methodology, the simulation results, and finally state my conclusions. So the problem, so our planet, we all know, is heating up fast. The average global temperature on Earth has increased by a little over 1 degree Celsius since 1880, with 2/3 happening since 1975. Now, this warming is primarily caused by increased greenhouse gas emissions resulting from human activity, and 39% of CO2 emissions can be attributed to the built environment. We see the world is facing the visible signs of climate change with increased frequency and intensity of extreme weather events, making it clear that climate change is posing severe threats to humans and other species survival. Cities are further impacted by the urban heat island effect, which is defined as higher temperatures registered in urban areas and in their corresponding surroundings of urban and rural areas, and they're in part due to land surface modification, human activity, vehicles, buildings, and materials. And this, as a result, is deteriorating the thermal comfort, it's worsening air quality, increasing intensity of heat waves, affecting people's health and well-being, and increasing the energy consumption. Now, with 140 million buildings already in the USA, it's not only important to shape the way we build and design the new structures, but it's also vital to fix the existing stock. And what better place to start than our homes, especially seeing that the residential sector is responsible for 16% of the total energy consumption, and most of it still comes from natural gas in the US. Now, 32% of the residential electricity consumption could be attributed to the HVAC system. And in the US in 2015, 1 in 3 households reported facing a challenge in meeting the energy needs, and 11% reported keeping their homes at an unhealthy and unsafe temperature, further stressing the need to find different ways to mitigate the energy demand, especially for cooling and heating in homes. So again, as cities increase their built-up area and expand to accommodate more people, space for nature is diminishing, and that's inevitably disturbing the city's ecological structures. So as I mentioned, we have more cities, more people, less nature. This increases the UHI, increases temperatures all the way up to increasing climate change. What I'm proposing is try to bring nature back into our cities to try and reduce that UHI, reduce the temperature, so on and so forth. Greenery has many, many benefits, from reducing noise pollution, improving air quality, mitigating UHI, stormwater management, absorbing CO2, improve urban environment, improve thermal comfort, reducing energy consumption, improve people's health and well-being, and improving urban biodiversity. However, finding ways to integrate nature back into our cities has proven to be challenging. And green walls are a great option as they have the potential of saving valuable floor real estate. There's really 2 different categories of green walls. We have green facade and living walls. Green facades are defined as all facade greenings that use self-climbing or self-hanging plants, whereas living walls are human-made, more complex systems, which are usually more difficult to maintain. They're more expensive. So I propose to focus on the green facades. There's already a plant in nature that grows vertically, so why not take advantage of that? So I propose to bring greenery back into our cities with green facades. I am going to analyze it both at a neighborhood scale, or more of an urban scale, and a building scale. So for my case study site, I've selected Austin, which, as everybody here probably knows, is classified as humid tropical, which has long hot summers, short mild winters, and warm spring and fall transitional periods. The CDC projects that the number of days in Austin, number of days above 37.8 degrees Celsius or 100 Fahrenheit, is going to increase from 17 to 29 in 2084, further stressing the need to kind of find ways to tackle the cooling loads. Now, the selection of the case study location was based on identifying residential neighborhoods most vulnerable to heat. And for that, I used a multi-risk climate vulnerability assessment for Austin developed by Victor and Yang, who identified these neighborhoods. Afterwards, I overlaid the current zoning to try and identify residential buildings and residential areas. That gave me this 26 census groups, 26 residential sectors. And by determining the mean of population and mean residential units, I selected this site, which is close to downtown, which kind of reflects that mean population and mean residential number of units. This area is confined by the streets of Cesar Chavez, Pleasant Valley Road, 5th Street, and Chicona Street. And as you can see, the prevailing zoning is single-family residential, but it still has a section of commercial, particularly along Cesar Chavez, and it also has a park on the top left side and the school, and also has a little more of a commercial and even industrial area next to 5th Street. For the neighbor scale and for the analysis, I mainly focused on the area on that area on the top left, because I wanted to understand, while I'm looking at the residential sector and how this added green facade would impact a single family home and a single family predominant neighborhood, I also wanted to understand what this park and what this other uses and how they would impact those areas. So for the methodology, I used EnviMed software, which is a three-dimensional grid-based microclimate model used to simulate complex urban environments. It's based on fundamental laws of fluid dynamics and thermodynamics, and can simulate the dynamic interaction between plants, buildings, and the atmosphere on a microscale level, which allows to analyze both a whole city and a single building. This software was developed by Michael Bruce in Germany in 1994, and since 2011, more or less, the number of papers using this software has increased. So I really have two different models. There's one neighborhood model and one building scale model. The neighborhood model, I have the baseline and then an intervention model where I added green walls to every single facade and to the entire wall. Now I know that's more than unlikely. It's pretty impossible to have every single building and no windows, no nothing, just green walls. But I wanted to really understand, taken to an extreme, I wanted to see how that would impact the relative humidity, the surface temperature, and the air temperature. And for the building, I have the base model and then 3 more interventions where I just wanted to analyze what would happen if only 1 meter of green wall was around the building, and then 2 meters, and finally the entire wall 4 meters. I am also analyzing this data at a pedestrian and at the building height. I wanted to understand at the pedestrian height what the impact of this added greenery would have, mainly for thermal comfort. And also at a building height, I wanted to compare the two and see if this added greenery could impact ultimately the building's cooling loads. So the neighborhood scale model, it's 100 by 100 by 25 grids with a resolution of 5 by 5 by 2, meaning each grid is 5 meters by 5 meters by 2 meters tall. And I identified different receptors with different points. So I'm analyzing the data, so the air temperature as a whole, what's happening throughout the model, but I'm also analyzing in detail in these different locations what was happening to try and see if the air temperature closer to the green wall would have an additional impact. And I'm also identifying, I've also identified this other places to analyze the facade to see the surface temperature. For the building scale, I modeled a single family house, which was the typical dimensions found in the neighborhood I selected. I've modeled also the surrounding or section of its surroundings, so a section of the buildings that surround this single family home, and added greenery all throughout the different walls. I didn't add a greenery, so most of these houses have front and back porches. So I didn't add greenery in those points, but everything has a green wall at a 1 meter, 2 meter, and 4 meter. The dimension of this model is 45 by 80 by 30, and the resolution in this case is 1 by 1 by 1. I've also identified these different points to further analyze. And so all the models were set to run for 24 hours, starting at 7 a.m. on July 18 with simple forcing boundary conditions using self-defined minimum and maximum temperatures at 25 and 239 degrees Celsius and wind speeds and direction of 2.5 meters per second and winds coming from the south. So for my simulation results, I'm going to go over first what happened in the neighborhood scale and then the building scale. So for the relative humidity, nothing really happened overall. There's a slight increase in the relative humidity. And the slight increase, I'm talking about maybe the baseline had 50% relative humidity and the intervention had 52% relative humidity. And for the air temperature and surface temperature, I'm going to go over in more detail. This is showing the overall, so the temperature at the model scale. If you see in yellow is temperatures throughout the 24-hour period that I got for the baseline, and in green for the added greenery, or the intervention. You can see there's a slight decrease from 39.97 degrees Celsius to 39.93. It's not very significant, and then but a small increase for the minimum temperature from 28.32 to 39, sorry. And so the highest difference that I got, or decrease in temperature, was at 6 p.m. And so this showed a decrease of the temperature of up to 0.18 degrees at a pedestrian height. And at the building height, it showed a 0.16 degrees for the minimum air temperature and 19 for the maximum temperature. But I also registered an increase in the temperature, particularly at 7 a.m., showing at the building height of 0.17 degrees increase, which I was not exactly expecting, but overall it's not much of a difference. Now, looking at the particular zones that I've defined, I have somewhat higher differences. The maximum air temperature decrease was registered at a pedestrian height at 6 p.m. of 0.23 degrees Celsius, but I also got that increase in the maximum air temperature registered at a pedestrian height at 8 a.m. You can see really how that fluctuation is a little bit higher, but I still have an increase and decrease. Now, where things get super interesting in a way is in the surface temperature. Here, I did get a maximum surface temperature decrease registered at a pedestrian height at 4 p.m. of 5.10 degrees Celsius, and only an increase in the surface temperature of 0.68 at a pedestrian height. You can see here things get a little bit more interesting. The green wall is really reducing that surface temperature, and especially in the west and east facade. The north facade is not as affected, but still has a reduction. Now for the building scale, the same thing happened for the relative humidity, really no significant increases or decreases. And for the air temperature and surface temperature, here I go into more detail. This scale showed practically the same numbers. For, again, in yellow, I have the baseline model, and then in green, I'm only showing the results for the 4-meter high greening of the facade, because the 1 meter and the 2 meter didn't show any differences really in the air temperature. And as you can see, the 4 meter is not really showing, it's just showing one slight reduction here at 38.23 to 38.22. That was at a pedestrian height. Now at a building height, everything is running slightly cooler. But again, the differences were non-existent. The air temperature is still basically the same. It runs a little bit higher in the morning, higher temperatures. But overall, the building temperature is running a little bit lower. For the zone air temperature changes, the maximum air temperature decrease was registered at a pedestrian height at 6 p.m. of 0.22 degrees, and still a maximum increase at pedestrian height at 10 a.m. of 0.06. So in this case, you see that, and I'm really not adding any greenery elsewhere. There is more of the improvement and the reduction is still not very significant. It's still just 0.22 degrees Celsius, but that increase in temperature is no longer as significant as it was for the neighborhood model. Also, another thing that we can see here is that the receptor R25 that I have set up more by the sidewalk and further away from the building really didn't show any variations. I'm guessing just closer to the building, the more it shows those differences in the air temperature. Again, here are the thermal maps of the air temperature at 6 p.m. at a pedestrian height, and you can clearly see how around that west facade going to the north facade and going back to the east, there's a cooling effect. The south facade and the front of the building is really not changing much. For the surface temperature changes, I got similar reductions of 4.81 degrees Celsius registered at the pedestrian height at 2 p.m. and an increase of 0.69, this time at the building height, found at 6 a.m. Which was, again, pretty interesting to see how this is impacting it a lot more. Now, for my results, so overall, what I found out is that there is a surface temperature decrease, especially between 12 and 5 p.m., with a maximum surface temperature decrease I registered at 5.21 degrees Celsius. But there's also more of a night surface temperature increase, registering a maximum of 0.69 degrees Celsius of surface temperature increase. And as for the air temperature, it decreases between 4 and 8 p.m. on average, and with a decrease of 0.23 degrees, so the maximum air temperature decrease I found. But it also increases up to 0.20 degrees Celsius, primarily at night. Now, this research aimed at studying the summer cooling effects of green walls to reduce UHI, improve thermal comfort, and increase the potential of natural ventilation and reduce the building's cooling loads. Now, I know that the reduction of UHI was not exactly as prominent as I thought it would be, since I'm getting only a decrease of 0.23, but I'm also getting an increase in temperature. Now, adding the green wall seems to reduce the surface temperature during the peak hours when the energy demand is at its highest, which could help reduce the stress imposed on electrical grids and diminish the likelihood of power outages caused by this demand surplus. And also the surface temperature reduction indicates that the greenery is protecting the building facade from the heat and reducing a building's heat absorption, which could potentially reduce its cooling loads. Also, studies have found that managing to reduce a building's heat absorption from the surrounding environment can significantly improve the cooling potential of natural ventilation, which could therefore be something that could also be integrated with this vertical greenery. And well, while I didn't get exactly the reduction in air temperature, especially that I had anticipated, let's not forget that adding greenery to our cities, still it really improves the urban environment. It can reduce noise pollution, improve air quality, improve urban biodiversity, improve people's health and well-being, has many, many other benefits. And for future research, I'd be very interested to do field measurements to validate the simulations and see what's really happening. I'd like to analyze other mitigation strategies like adding trees or green walls or a combination of this, which have studies have shown that they have quite a cooling or added cooling potentials. Like to simulate the building's energy loads to see how that reduction of that surface temperature would impact, really truly impact the building's energy load. Another mitigation strategy of the sort would be to add a second facade in a way to kind of amplify the number of buildings that could have a green wall shading their facades and see what the effects of this would be. And I would also like to analyze in more detail different building materials to understand how a green wall has different impacts depending on the materials we're using. And that's it, pretty much. Thank you very much.
Thanks, Maite. I have a quick question to do with parameters, and I apologize if I missed this. What day, you were analyzing a 24-hour period. What day of the year was that? That was.
It was July 18th.
Why July 18th?
July 18th to try and get, well, the 18th was trying to get the July in the middle of the summer. Gotcha. It was also in 2018, which had some of the highest temperature registered.
Yeah, and I asked just because one way to approach it might have been to choose an equinox, and I wonder if even if you were doing more work on this, perhaps just equinox, because when you mentioned that sometimes the temperature, it did some temperature increases, I was thinking, well, perhaps this is far enough away from the summer solstice that it actually is working a bit in reverse and just generally flattening the extreme deviations that we have between heat and cold. And so I could almost imagine, or perhaps even if you did the winter solstice as a separate analysis to begin to look at that, that might be an interesting component as well, that it's not just about managing heat, it's also about managing cool, perhaps as well, as another layer to this. So that was more of a question than it was just a comment because I didn't catch what day it was.
Well, I wanted to jump in here and just say, first of all, I think you're making real progress. This has really become much clearer, much more focused. I think the process has been defined. I think your results are interesting. I just might say, you talked about field measurements. I've been doing some research this last year for a paper I'm trying to put together on microclimates, and have some findings that bring some questions that I might ask for you. One of the things that so far that I've found is that, wow, what a big difference in microclimate there is than what we currently are using in software programs for indoor and outdoor temperatures in terms of design. I think it has to be based more on microclimate now than it does on sort of regional temperatures. One of the things that I found is, of course, that the relationship between the building configuration and the microclimate is huge. And you can see that, I think, in some of your analysis. What I found is, of course, the major factor in that is shading, and that changes throughout the year. So you need to look at that throughout the day and throughout the year. The second one, which was surprising to me, was the exfiltration of air conditioning from the downwind actually modified the microclimate quite a bit. I think some of your, if you look at some of the aerial thermal photographs, you can begin to see that. And has everything to do with the thermal temperatures adjacent to it. In this case, leaking air conditioning coming out of the building actually provided a different temperature directly. The solar temperature directly outside was quite a bit different, which was surprising me in some of my findings. The third one was the surface temperature of the Earth. Earth temperature surrounding your different buildings was drastically changed throughout the summer and really affected the microclimate temperatures. So I think it's a great idea to try to do some calibration of your findings using some field measurements. The other thing I would say is in the green wall, I think, as I was saying, shading seemed to be the biggest factor in changing the microclimate. But I suspect the green wall does more than just shading. I think there's a change in state, and that is that the plants are transpiring the heat. There's a heat that's been going through a change of phase here, so it's being absorbed and transferred into moisture, which in somehow you want to measure that kind of effect to it, because I did find as well, if you change the humidity level in the microclimate, it has a great effect on variations in microclimate as well. So maybe when you go back in and lay out the preambles of your research, you can begin to talk about the dual nature of the green wall in terms of shading, also in terms of its transpiration.
Yeah, definitely. Thank you.
Yeah, I'd like to add something connected with that. I feel there's very interesting ideas in the presentation. I'd like the connection with the social vulnerability index, right? I think that is important. It's, working with, and I would even maybe compare that, and I'm not, well, this is the final, but, compare that with other neighborhoods. But one thing, I've seen a lot of work with the NVMet program. I think it's, I've heard it's really powerful. I have not used it personally, but one thing that might be missing, and maybe I missed it, is sort of the, how we actually feel in the outdoor environment, which is, it's not just temperature, but it's thermal comfort, right? So the effect of the green surfaces, when you were looking at the temperature, you found that they were very similar, but maybe how we feel in that space is actually very different because of the surface temperatures of the green walls, right? Because they could be significantly lower, and we are not going to have the long wave radiation coming from these walls, right? It's going to be more, as Michael was saying, is more like another type of effect that is actually cooling. So I feel that, it'd be interesting to see how we actually feel with the temperature, with the radiant effect, with the air velocity, and the relative humidity. And I think the results would actually be more conclusive towards the benefits of green surfaces than just looking at temperature.
Yes, I completely agree. And that's also part of the reason why I was looking at the air temperature in the model as a whole, and also try to pinpoint these different locations located close to the facade to see if that yielded some different results. And the reductions in the air temperature were still not great. It's still just maybe 0.20 degrees Celsius, but they were higher at those points than what I found in the overall kind of temperature of the model. But definitely looking and NVMet can look at does show the air velocity and has many other aspects that I didn't really dive into, but analyzing all of those to truly understand what that space feels like would definitely be something very interesting to do. Thank you. And something I'd like to do.
Michelle, I see you have your hand up. Thanks, Pablo, for that comment.
The first one's a question of clarification. I looked up, is it NVMet or OnVMet? But just from the general description of being Reynolds average Navier-Stokes, my impression is that it's a finite volume, fairly large grid. Unless you know the size of the grid, or were you able to modify the size of the grid?
I did specify the size of the grid. So for the larger model, the size of the grid was 5 meters by 5 meters by 2 meters tall. And I also defined the boundaries of the entire model, whereas the smaller building size was 1 meter by 1 meter by 1 meter. I don't know if that's what you referred to.
Yeah, that's what I meant. Yeah, which is one of the things that kind of configuration we find is good for is actually wind. So you can operate at a grid size like that for wind, and you can use a finite volume model when you're dealing with wind. It's actually pretty good. Natural convection needs a much smaller grid size, and radiation the smallest of all. So we do have different kinds of functions that we insert into our CFD models to kind of, in the same way we do lighting analyses, we tack in luminosity rather than actually sort of track photons. And we do the same thing with these models to get a general approximation of radiation and a very general approximation of convection. But on the whole, they're not that accurate. The accuracy which you're reporting your results is below the accuracy of what you can get at the grid size that you're working with. And that's nothing wrong with the modeling, because I think the modeling reveals an awful lot that's really quite interesting. But what I would and I'm glad you actually know what size your grid is, because a lot of people I talk to would not know that, particularly coming from our set of fields. The part that I'm going to ask you to do now, are you thinking about going on to do a PhD?
Not right away, but it's definitely not something that I'm not closing the door on. It's something that I would potentially like, yes.
So this is sort of how you might take this and think about the next steps, is to be able to ask why. Why am I getting these results? What is the phenomenon that's driving these results? So as a good example, exhaustive studies have taken place now for a couple of decades, slightly more than that, about green roofs. Mm-hmm. And what is the actual mechanism of a green roof that's making a difference? And it comes down to, there's actually two mechanisms, and none of which we thought those were the mechanisms. One of them is a fairly basic one, in that it's additional insulation. So, it's a really expensive, but additional insulation. And the other one actually has to do with the leaf canopy. So, that there has to be a differentiation between sort of like the surface and what would be a canopy. So certain plants actually are providing shading, other plants are not providing shading. So it is that. But, most of the impact or the most effective things that we tend to see for urban heat island are things that deal with emissivity. And, on the whole, green materials are not great for emissivity, but there's other things that they can do. So even coming back and said, is this a product of shading? Is this a product of insulation? So one of the things that we think about when we think about urban heat island are point sources of wherever we've got a condenser, sort of exhaust is not the right word, but a heat release on it. If we start thinking about the fact that we're kind of managing these different kinds of point heat sources on buildings, is that what this is doing? Sort of like dealing with the building is not radiating its heat to the atmosphere, it's radiating its heat to this particular green layer, which is then affecting sort of like the relationship back. There's a lot of things like that. See if you can start thinking about what these different mechanisms might be, because it might tell you, okay, just paint it white. It might tell you, actually, the green is great, but the green only needs to be here. It probably should be 2 feet away. It only has to be on one side of the building. In our emissivity studies for urban heat island, we found that you only have to deal in urban areas, you only have to deal with the top 20 feet of a building. The rest of it doesn't matter. So there's a lot of things like that I think that I'd love to see, because the analysis was fabulous. I loved how you went through this analysis, and really excited me to see you using this tool and using it with such great competency. But then start saying, what are my questions now? Now that I have this, why is it like this? What might be happening to cause that? So yeah, do a PhD. Yeah, think about it.
Thank you so much. Yes, definitely understanding the why is very important, something I'd really like to understand. So thank you very much.
And to that end, and kind of following up on some of Dean Addington's comments, I've got also a couple of clarification questions and then maybe a comment in response to that. But the two of those were, when you were finding I think you phrased it as the temperature at pedestrian height. Was that a radiant temperature or a mean radiant temperature, or what were you measuring there? And then the second one is that I'm not familiar with that off the top of my head, that particular block, but I know that general neighborhood has a relatively mature tree canopy. And how did you model or deal with the existing trees that are already there in relation to your addition of the green walls?
So the trees in the model, that was a little bit difficult, and to try and understand how many trees should I leave out and have more of a kind of an idea of that neighborhood was a little bit of a dilemma. But ultimately what I did was to try and add all the trees that were there, or as many trees as that was possible. And one limitation that MVMet does have is the time it takes to run the simulations. So for the neighborhood simulations, if I'm not wrong, it took for each one about 5 days to run. And for the smaller scale, it would take around 2 days to run. By adding larger trees, you're ultimately adding more information to more cells in the vertical sense. That was also really impacting the time it would take to run the simulations. But ultimately, I did try to add as many trees and try to add as much of that green cover as possible. That's why also analyzing or integrating more trees and looking at that mitigation strategy would be very interesting. So that's kind of what happened a little bit with the trees. Probably there are more trees than I actually added in the model. Now for the temperature at the pedestrian level, it's still the surface, just the air temperature that the model was registering. But instead of, you can define exactly at what height you're finding that air temperature. So I guess, yes, it's not necessarily the radiated heat or anything.
Oh, okay. So I was, I don't remember now exactly the terminology you used, but there were, when you showed us the graphs, we were seeing mainly a very small differential on the order of plus or minus 0.2 degrees Celsius. But then in some cases, you were measuring a temperature where it was up to close to 6 degrees Celsius drop. What was the difference in those two cases? And
the difference was the air temp. So the air temperature overall didn't show any or much of a reduction, all the way up to like 0.20 degrees Celsius. That was the air temperature. And then the other one was directly the surface temperature that is registered. So that is kind of the difference between the two.
oh, God. Okay. So surface temperature of what surface? Is it average of all the surfaces or the wall?
Of the building, of the wall.
Of the building. Okay.
Yes. At a
Got
specific point. It's the temperature at that specific cell that I chose and defined.
Ah, okay. I see. So it's an impact on an actual pedestrian it's hard to say, but probably fairly minor, because they're going to be some distance from the wall of the building itself and probably minimal impact on their radiant experience there. So operative temperature of the pedestrian probably doesn't change all that much.
So yes, those are the three different measurements. So there's the temperature overall in the model, the temperature right next to the wall, but that's still the air temperature, and then the temperature on the surface of the building. That's more to understand more from a perspective of the kind of cooling loads, and if there was any reduction for the cooling loads of the building, is how it's impacting the building more than the pedestrian really.
Gotcha. Okay. Well, and so I think I agree with the previous comments that you went through a very thorough and impressive analysis, and it's really, really interesting. I guess I would maybe, I guess what I'd like to see is you taking a little bit more of a firm stand on the outcome. And, you know, it seems to me that while this is really interesting, it's kind of also like, well, gee, it was kind of disappointing in how effective this is. That doesn't call into question. That's a perfectly valid research result, and important, in fact, research result. Like going back to the green roof studies that Michelle was just referencing, you know, there was so much hoopla about how green roofs were the panacea for all building problems, all this stuff, all this evapotranspiration and all this stuff, you know, 15 years ago. And it turns out that they've got some good qualities and they are beautiful, no doubt, but they definitely did not meet the level of hype over their performance impact that was put upon them at that time. And, you know, a lot of people spent a lot of money on something that really didn't live up to what it was supposed to do from a, you know, physical thermal point of view. So I think it's really, really valuable to, you know, to really study this stuff and figure out, you know, what the real world implications are. And, you know, so to the next questions, I think you've already hinted at are, okay, well, one, is this a effective use of resources? The social vulnerability index is a really great way to kind of approach, you know, thinking around this, I think. But is this, you know, approach the best investment in? Could you get the most positive outcome, best return on your investment using this approach? And it seems like your results, I would argue, say, well, probably not. This doesn't seem like it's going to have enough impact to really justify that. However, there are a couple of factors. One, the trees. You know, if we're talking about, you know, brand new development where there isn't an existing tree canopy, you might have a completely different situation. Or maybe it's that the wall isn't quite the right answer because there are other things like eaves, cool roofs, trees and so forth that could achieve similar results. But we might focus our efforts on, maybe low impact site development strategies like rain gardens and whatnot that take, part of the public right of way and put more greenery out there to deal with stormwater problems. Maybe they can also have a significant impact from a heat island point of view or something like that, and where you can use the same tools to study the other permutations of the way this kind of idea might be applied and maybe get a more dramatic, result. But that doesn't at all call into question the research, but I think it was very nicely done and really informative.
Thank you so much. And yes, looking at different mitigation and the combination, especially, I think that's also the best way to in a way go about it, because just adding green walls or just choosing one single mitigation strategy for anything, I don't think is the answer. I think the more and the wider variety of different alternatives we have, the better it is. And if we're able to measure and see which one yield the best results and which combinations maybe have the best or similar results, you're also giving much more kind of that wider array of possibilities, which is always more beneficial.
All right. So, Dev, I wanted to give you a chance to make a comment. We tracking on time. It would be good to stop in the next, let's say, minute or two to then have our next presentation will be at 4 o'clock. If we have a little break before that, and if a couple of minutes would be sufficient for you, Dev, that might be a good stopping point for us to reach with Maite's presentation. Go ahead.
Sure. Thank you. Two quick things. One is I love the infographics. I think everything you put there is so memorable. And because of that reason, I'm going to caution you not to put that 5.6 degrees Celsius as a conclusion, because if you recall the discussion, that sticks out. And that is not really what you found in your conclusion. It was at one location where you did it. I sort of wanted to reflect on the previous comment. You have done an analysis, which is fantastic. I mean, I love the fact that you guys are using EnviMet. I come from a large scale urban weather perspective using weather research forecast kind of models. So in the context of that, you've done it with 1 day, with one orientation for one region. So I hope we don't provide the definitive conclusion on this, that for Austin, this is not going to be working. So it'll be really good to lay out the constraints of what you've done and why the limits exist. The second one would be with regards to the winds and the other factor, the feedback. That is really going to be important, and we can talk a bit more about that. But what I really want to understand is, how did you change the greenness fraction in the walls? Is it like you went in and changed the emissivity, the albedo? What did you do in the model?
EnviMet allows to add, so EnviMet, the latest version of EnviMet actually added that function where you can add a green wall directly on the facade. And it's the software in a way is already doing all those calculations. So I'm not modifying anything from the wall. It's already done, and I'm using all of the sort of the default parameters from the software.
Fine. I think I'll follow up with you more, but I just wanted to say there was a lot of question about verification. This summer, we have a NOAA project which will be doing Austin heat mapping. So you'll get a lot of data, and we just finished some of the NASA developed study for multi-sensor satellite-based heat island mapping. So you may want to look at this year rather than the 2018 to try and see what we can find to see that, or maybe in the follow-up. But nice work, and thank you.
Thank you. And yes, it's definitely looking at a much smaller microclimate and not something to take and understand as a general scale. Yes.
Thanks, Deb, for the comments. And I think we'll conclude there. I wanted to comment really briefly, Maite, as we wind down from your presentation and discussion, that you really did have a huge leap between Thesis A and Thesis B. I congratulate you on the work. I think that at thesis A, at the end of thesis A, there were a lot of questions as to what you might pursue, how you might actually bring this to something that might have rigorous data. There were, the funnel was quite wide at that point, and you did a good job of bringing it down to something, and still acknowledging that this is one of many different approaches you could take, and much of what you're proposing is somewhat of a retroactive or reactive appropriation. But regardless, you took to heart the reviewers' comments from thesis A and really tried to, it really advanced this to something as a very conclusive and comprehensive thesis work. So congratulations on that, and congratulations to the committee as well. Is there any other last comment from Maite's project before we take a break to then resume at 4 o'clock for Cole's presentation?
I'd just like to say thank you for our external reviewers. You're welcome to stick around for what we call Thesis A as kind of a mid-review of current thesis students. So we'd be glad if you all could stick around for that too. But thank you so much in any case for your attendance to these final thesis presentations.
Yes, thank you all. All right, we'll break, and those of you that can and are interested, please do join at 4 o'clock when Cole will present his thesis A work. Thank you all, and congrats, Mike.
Thank you. Thank you.
Great work, Maite. Great work, Ben.
Thank you.
Hi, Cole, just as a general note, I just mentioned that we have a 45-minute window for your presentation and discussion. And so obviously it's up to you in terms of how long you want your presentation to be. I would generally recommend trying not to use up too much of that time, since this, to allow some room for discussion and comments and questions after. And so just wanted to mention that, especially being thesis A, where you're obviously going to build upon this work, and it's important to try to get some feedback that at the stopping point. So I just wanted to mention that. I'll say the same thing to Young Lee when she's kicking off, and Young Lee might have heard that as well, but hopefully so. So anyway, whenever you want, Cole, you can go ahead and share screen and then we'll kick off soon.
Is that good? See it?
Yep. Okay. Yeah, they can see it just fine. Oh, hi, Alex.
Hi, Matt. Hi, everyone. I'm right on time, right?
You are, right?
Switching from one review to the other.
Yeah, we understand how that goes. So yeah, we had to we shifted a little bit of the earlier sessions, but caught up to on time at 4 o'clock. And so Cole's just about to kick off. Actually, yeah.
Perfect timing.
And go ahead and begin.
Okay. Well, thank you. I'm excited to be here. First, really quickly, I just wanted to offer my congrats to my peers, Ben and Maite. I don't think any of us had any idea of the challenges that were ahead of us when we started all this. So it was just really impressive and encouraging to see the finished product from those two. So congrats. And I'll jump into my Thesis A review, which is Urban Food Recovery Analysis and Opportunities. And thanks to my advisors, which are Dr. Liebernicht in the School of Architecture and Dr. Metcalf in the School of Human Ecology. The agenda, what we're going to talk about, I'm going to spend the first part sort of just making sure we're all on the same page as to where this research is coming from, talking about the problem and just sort of setting the table, if you will. And then I'll jump into the research question, the methods, anticipating findings and next steps. So to start, really what started me thinking about this research was urban ecosystem flows and urban ecology. And this very simplified diagram just shows basically that resources flow into the city. All kinds of things happen to them while they're in here. And then they flow out as waste or emissions. So I'm particularly interested in food. It comes in, it's transported, stored, eaten, prepared, and thrown away, either as organic waste or sometimes in the wastewater. And so, as we all know, cities are growing in size and in terms of the percentage of population that lives there. So I think it's really important to understand these flows. And so food and waste are the flows I'm focused on, and 35% of food is wasted is really one of the main issues. And when food is wasted, it wastes all the other things, all the other inputs that was used to grow it. So the water, the land, the labor, the transportation, all that is wasted when you waste food. And as you can see from these charts, a huge amount of it is ending up in the landfill. And that creates methane emissions. Food waste is responsible from 6 to 8% of total greenhouse gas emissions, a little bit less in the United States, but still a significant amount of greenhouse gas emissions. And on the right, this is just showing where food waste comes from. There's a lot of different reasons for it. A huge chunk is simply just excess food. Spoiled date label concerns are some of the other ones. But basically, I think what this shows is that it's an inefficient management of this flow. We're wasting too much of it, and it's causing these other problems. So to zoom in a little, I'm trying to focus on retail food waste, which is basically distribution and grocery stores within the city. And although their slice of the pie is a little smaller, it's still 10.5 million tons of food waste per year. And of that waste, this is sort of the destinations for it. You can see that a good chunk is being donated, but a lot of it, 3 million plus tons is still ending up in the landfill. And why is this important? Well, the EPA has put out a food recovery hierarchy that says the most preferable way to reduce food waste is through source reduction. This is hard in the retail environment, and I've learned this through some of my interviews that really you cannot, the excess is necessary from a business perspective, because if HEB or Walmart or Amazon calls you and you're a supplier and you don't have the food they need to meet that order, it's basically a death sentence for your business. So you have to have the food on hand, and that creates this surplus, this excess. So that's a really hard problem to solve in retail. So go to the next step, which is to feed hungry people and by donating this food. And right now there's 42 million people in the United States who are food insecure. And with all this food going to waste, it's sort of unacceptable to have that amount of hungry people. So that's what we're focused on. And the food recovery supply chain is what's currently doing this in cities. And so on the left side, you have your food sources, farms, processors, retail. Again, I'm focused on these distributor and retail environment right here. You have reasons why the food is not sold, some of which deterioration and quality require that it be wasted or go to non-human use immediately. Other reasons are strictly market-based, and the food is still perfectly fine. And that's when the food rescuers come in. You have your traditional rescuers, which are food banks. You have complementary rescuers, which are sort of like apps or technology that's coming in to assist in rescue, or the original food source, which would be like HEB rescuing its own food and reusing it for another reason besides selling it in their stores. The next piece, number 4, is you have value added. Sometimes you do, sometimes you don't. Traditionally, food banks just rescue the food and redistribute it. Soup kitchens would be an example of value added. They take the food and they prepare it into something like a soup that's adding value to the end product. And then it gets redistributed through food pantries, soup kitchens, or complementary orgs, or surplus grocers, or even sometimes this perfectly edible food is sold at market price or higher. And it ends up to people with food insecurity or without, depending on which route it's taken. And this chart is just another way of looking at it that I like, this infographic. You start up here with your manufacturers, distributors, grocery stores, and then this is the food bank. And this says hundreds. This is from a local New Mexican food bank. It's really thousands of pickups per day that's happening. Most food banks have their own fleet of trucks that they're doing this with. And then on top of that, there's volunteers out in their cars who are also going on a daily basis to grocery stores and picking up food. It's all taken to the food bank, where this functions as a warehouse. It's not really a retail center. It's more of a distribution point, where volunteers, sort, label, box repack, and then the edible food is distributed through food pantries, shelters, and other things. And what I like about this comparison is really you can see that the food recovery supply chain is almost the same as the retail food supply chain. You have the distributors, which is the food bank, and then you have the sort of retail outlets, which is the food pantries, and then you have the customers. And so they're really a mirror of each other. One is just charitable food, and one is based on the market. Let's see. So food recovery research, the first food bank was, I believe, came about in the 70s, and we have about 80 published articles researching the food recovery supply chain. And here on the left, you can see a breakdown of what they were studying: measures, interventions, and outcomes; mathematical modeling, which is using modeling techniques to explore, patterns or dynamics that are going on in the city; literature review; and then a couple that didn't measure intervention or didn't measure outcomes. And then on the right side, these bullet points have really been identified as the issues with food recovery research right now. And that it's inconsistent for reporting and evaluating outcomes. It can be in terms of food saved, meals served, people served. And so there's a few different metrics. It's kind of all over the board. And same thing with nutrition, environment, and financial. They don't track food flow very well. They don't track other outcomes. So importantly, the main outcome is to bring people out of food insecurity. And a lot of times they're just measuring how much food is going through instead of, the main point of these things. And then the last one, just to continue to perform more in-depth and qualitative and quantitative assessments. And so these are the things I'm keeping in mind as I do my research. The research question is, what are the most significant barriers and challenges to increasing the amount of food recovered from retail food outlets, and what interventions are currently being used? So the methods is a series of surveys and interviews. And the interviews, I've already done several of these with people at the city, people at the food bank, people at food pantry, and a few of these sort of alternate companies that are really sort of tech startups that are trying to capture more food. So that's where I started with the interviews. That led me to creating the surveys because I just wanted to access more information from more people. So last month, I was able to get IRB approval. They determined that this is really gathering information and not opinions. So I went through that process and got approved. A lot of the work has been focused on asking the right questions, right? So what are the important outcomes? What are the important interventions? And what's the best way to sort of measure those or to get those out from the people working in this supply chain? And the surveys are really meant to go to two places: food banks, which I'm working with the National Organization of Food Banks, which is called Feeding America. There's over 200 food banks in their membership organization. And then another, a food bank in the Northeast that's really active is called Food Share. And I'm in touch with them as well to sort of help me refine the survey and to help me distribute it. And so feeling good about that. The retail outlets have been much harder to reach. I'm still in the process. I have a few leads out, but they are more hesitant to speak about this information and to give away their data. I think they're a little bit afraid of bad public relations coming from, wasting too much food. And so, I'm still determined to survey these folks. But if not, the research will just focus on food banks. Well, I think that'll be important. But I think that I'm determined to still pursue retail outlets, even though it's difficult. I think the fact that the information is difficult to get just indicates that it's important research. So that's one of the issues I'm working on. And then lastly, to spotlight Austin, Texas. So using the survey data and the interview data and some data that I think they're going to share with me about the amount of food going from each retail location and going to each pantry from their facility will give me a chance to sort of map the flow a little bit. So the surveys for food banks, I'm looking for 25 at least. I think that's going to be really achievable. I'm optimistic right now that there's going to be more than that, but 25 would be a good number. The main questions in the survey, they have to do with challenges and interventions. And as far as challenges, there's 5 main categories of challenges that have been determined by the research. And within these categories, there's subcategories. So when they take the survey, they're going to rank these overall, and then they're going to rank the challenges within these. Interventions mostly fall into 3 categories, which is transportation, which is third parties collecting or redistributing. There's processing interventions, and there's coordination interventions. And so those are the questions that are going to be on the survey. And this is all through Qualtrics, I should mention. And then the surveys for retail food, they look a lot similar. The number is a lot less. Like I said, it's been a real challenge to engage with these folks, at least at the beginning, but I still am determined and optimistic to find someone who's going to work with me on this. And the main questions are the same. The challenges in the retail side are a little bit different. Although there is some overlap, they don't have the exact same challenges as the food bank has. The main problem there is there's not much incentive for them to donate the food. It can be cheaper for them to just throw it away. So that's the surveys. The anticipated findings look like this. This is not real data, but you can imagine once I have the survey from the retail food managers, I'll be able to rank the challenges as to why they're not donating a higher portion of their food. Same thing with the food banks. I'll be able to rank their challenges and see if there's any consistency among food banks or if it's really sort of all over the board and each food bank has its own individual challenges, based on specific circumstances. And then the interventions, be able to see what interventions are being used in retail and what are being used in food banks and how they compare. So that's all, hypothetical. None of that was real data, as I said. And then for the Austin part, it's really taking all the data, the challenges from retail, the challenges from food banks, the interventions measured, and then the retail food donation statistics, the actual data, and analyzing what's happening in Austin with the Austin food recovery supply chain. And ultimately, that will take shape of a GIS map. And this is one from the city that shows all the food assets in the city. So the red, I believe, are the retail. The purple are the food recovery. And so you can see they're sort of dotted all around town. The food bank's down here somewhere. And with this data, I'll be able to show, approximately how much food is coming in to the city, to these retail destinations, how much is then going to the food bank and then being redistributed to the purple, the food pantries around town, which I think will probably illuminate a lot of, inefficiencies and just add to some questions about why stuff works the way it does. Next steps, continue the interviews and administer surveys. That's May through September. Keep working with the Central Texas Food Bank to get the data for the retail stores. That's June through September. Analyze results and draw conclusions next fall. So here are my references, and thank you.
Thanks, Cole. I might start unless someone else wants to jump in. I'll go ahead and start. So I think that I think that there's plenty here to work with in terms of that you have a strong start to your thesis and you have some clear ideas of what it is you're interested in, and what your methods might be. And I think my main recommendation would be I think the way that you set up your question was to identify barriers and effectively identifying or critiquing the existing system. And I wonder if you maybe invert this, and there's a second layer to this. It reminds me a bit of when Bucky Fuller has a quote that says something similar to, you don't take down an existing system by just critiquing it, you just propose a better system. You could identify negatives of any type of system, but just propose a system that trumps that earlier system. You design something that transcends it. And that might be a way of thinking about this rather than identifying, well, here are all the barriers, here are all the problems in this system, but instead proposing a new flow chart, a new way to think about it. And one reference I might suggest is a book called Cytopia by Carolyn Steele, How Food Can Save the World. And she's an architect actually, but has written about food systems historically and how food works within cities generally, especially talking about London. But that would be my main suggestion is thinking about when seeing your anticipated findings and those being very much matter of fact. Well, I'm expecting to see that these will be the comments that come out of it. I would hope that you would pull something out of that could transcend just the numerical responses and some data there and pull this out to something else that could be a pretty bold, a bold recommendation, a bold proposal that could be something you might never have anticipated before collecting all this data and synthesizing it. Maybe that's the biggest point I would have to make, just sort of synthesize all of this and really come at it with something original. So thanks, Cole.
Great, thank you.
Cole, I'm make sure I'm not muted. Am I muted? No.
No.
Cole, I'm preparing my studios for next semester, which we're focusing on food. And I've been working with HEB. And so I have some contacts that maybe help you. Brad Peace is the vice president of HEB, which is the head of the architecture. And we're working primarily on the upside, you know, of the farm to market, farm to table, I should say. And that is, you know, how the food gets to the food at the store, working with Gotham Green and some other kinds of things in the design of the store. But he might know who in the company could be the one to begin to talk about getting that resource to it. So I will talk to him, or I will give you his email address, and maybe he can be a source for the retail contact that you might need.
Great. That sounds really great. Thank you.
Yeah, just to follow up on what Michael was saying, I was also thinking of HEB. Of course, I didn't have the contact, so that's great. But I wanted to ask you, how you're thinking about the importance of the outlets that you would potentially survey. Are you interested in some kind of a broad range of different retailers who might have a different approach to sustainability? Or it's okay for you to just get data from HEB because they are massive? You know, I think it's also important to understand, because we know that the food banks, they have like one objective, right? But the retail outlets, they're very different. And some of them, like, for example, nature grocers that I know them because they are in my neighborhood, they're very concerned with that. Other stores will be less concerned. So I think that's an important also aspect to understand, so that the results of your survey in some way are either representative or just a sample. And I think you should be clear about what that is, right? At least that's just one thing that comes to my mind. The other thing I wanted to say is that Matt mentioned your question, and I was wondering about the second component in your question. Like, you mentioned the barriers, so understanding what's working wrong, but then you ask, what are the used methods? What do you mean by the used methods? Like,
so the interventions, well, right now my understanding is that there's various ways to sort of improve how much food is being donated.
okay.
But not every food bank and retail outlet are using these. And in fact, you know, I think very few are. Some of them are just doing it. It's really done on an ad hoc basis a lot of times. And so there's not a lot of structure to who's using what to improve efficiency.
Okay, so you're talking about understanding the existing methods, not a proposal, as Matt was suggesting, of other options. So, you know, I think what could maybe help also is to do a couple of case studies that are not from Austin, but are known as really successful systems in other American cities, or maybe even another place, I don't know, London, and look at, you know, or any other cities, and look at not just the methods, but, as you mentioned, what are the incentives? Like, what makes those places work better? And I thought that, you know, when you were mentioning incentives, and I don't remember what else was on that list, one thing that to me was missing is the regulations, and both the regulations that would impose food recovery, but also the ones that might be impeding it. I think that's an important thing to look at. What could be out there in the regulations in the city that is actually preventing, even if indirectly, these processes? And that might be actually surprisingly, those things, the regulations and incentives, could lead you towards some suggestions, proposals that would be more, you know, well, that wouldn't be just understanding what's wrong, but as Matt said, you know, being proactive in a way. And I totally agree. I think that would be fantastic to do that. So case studies could lead you towards understanding of what's out there outside of Austin, and what you could think as, you know, an option to implement here. Of course, understanding whether the contexts are comparable. But those are the things that come to my mind.
I'll just say
Yes,
that
thank
in France, they recently made it illegal for retail stores to throw
Exactly.
their food away. So
Right, yeah.
they're one of the leaders in this.
Yeah, but you might find places where there is a tax incentive on, a tracked amount of food that is diverted from landfill, and you get some kind of a financial incentive. I don't know what it is, but I think those are really important things to look into. Fascinating research to do. Great start.
Thank you.
Cole, the thing that really grabbed me as you were making presentation was the description of the sort of ecosystem of the producers, the retailers, and the redistributors, which maybe that's common knowledge. It was brand new to me to think of it in that way, and I think really fascinating, and kind of got my mind ticking on a bunch of ideas kind of at that level. And it brought to mind this book, which you might be familiar with, or maybe not. It's called The Goal by Elihu Goldratt. And it's this book about manufacturing constraints. It's like everybody having anything to do with manufacturing has read this book. It's a little bit cheesy, but it's actually has a lot of really great insight in it. It's kind of told as a parable, which is kind of neat, but also sort of cheesy. But the basic idea is that manufacturing optimization is not about if you try to optimize the entire system, it's doomed to fail, and that you've got to find the bottlenecks in the system and gear everything else in the operation toward feeding those bottlenecks to maintain throughput. And the reason that I thought of that was your comment about how the producers have to produce excess inventory that they know they're not going to sell to the retailers in order to have the supply on hand to deliver. So they're not exactly dependent on the redistributors, but there is like this nice dovetailing of relationships there, and maybe there's something to exploit in those relationships. So on its surface, my thought is maybe sounds contrary to Matt's, but I think the outcome is maybe in line with what he's suggesting, is that if there was a way to analyze this as a system where you could propose, whether it's a brand new system or whether it's tweaks to align the kind of incentives that Alex was talking about with, the interests of these different entities, in the supply chain, that could be really fascinating. I also recognize this is just a thesis, and you've got to be very directed, and you can't take on, solving all the problems of the world. But I think there's a really meaty set of relationships that could be thought about in a really innovative way when you're looking at it from that systemic perspective.
Yeah, I totally agree. And I don't think it's common knowledge that the food rescue supply chain works that way. I didn't know about it until I started this research, and most people I talked to didn't know about it. So I agree that thinking of it as a system might be uncover new things. So thank you.
Sure.
Yeah, I think those are some very useful comments. There's another layer to this that I'm not sure how you can address it. And I just noticed that Professor Liebernick just posted some comments as well, which are worth reviewing. But I was going to overlay another aspect that I hesitated to even mention, but I think it's critical because you brought this up in the beginning, is there's a cultural expectation that comes with a lot of this waste, right? This idea that we expect food on demand. We expect everything on the menu to be available every day of the year. And this is something that I think is more so the case in the US, and but it might be a larger issue. And I don't know if there's really a way to incorporate that, or if it's a matter of just acknowledging that as a limitation. I think somehow, I think that's an ingredient that has to be part of the ultimate conclusion, and maybe getting a bit of a sense of what sort of difference that makes. When you mention that leads to a lot of waste, I don't know if you have thoughts on that, Cole. Is that something that we, in your mind, that we somewhat accept as part of this, or is there any way that your paper begins to propose ways to perhaps set up a sea change in terms of a cultural perception of food and temporality, and see when things are in season or not, or those type? Again, I don't want to shake this up too much, but I feel that that's a very fascinating part of what you're dealing with that you brought up in the beginning. And it just got me thinking, that's a big part of the problem. And it's a bit like the energy problem that we have, right? We have this problem with everyone wanting it to be 72 degrees with a certain level of humidity all the time, and climate control. And that demand, we're trying to then find a way to increase, to deal with this, to supply that demand in terms of energy, and then make buildings therefore more energy efficient. But there's another way to think about that in terms of just setting up expectations that buildings don't need to completely control the climate. For me, it's a bit analogous. And so I don't know if you have thoughts on that, or if maybe that's just something for you to ruminate about as you continue.
Well, I think it's fascinating. I think that that's probably the key to what you said earlier about proposing a new system is, for the retail environment to look different, the customer first has to accept it. And so that's, to me, there's a huge opportunity for research there for retailers as to, digging into customer perceptions of maybe there's not quite as much variety or not quite as much quantity. And, does that make people not want to shop there? Will they lose a customer share if that happens? Or how much can they adjust? How much can they decrease and still retain customers, right? So
yeah, exactly.
Yeah.
I mean, I don't. It seems crazy, right? But we go to the supermarket and expect every vegetable and fruit to be available every day of the year. I mean, I don't even know when they're in season anymore. In my mind, I don't know when's banana season. I don't know. I just expect them to be there and to be perfectly. I say that admittedly being part of the problem that perpetuated that, and you expect to go to a place where you do have that variety, and so it is a large issue, and I'm not sure how much you can really tackle that, but yeah, thanks for commenting on that as well.
Thank you.
I was just wanted to make sure you had a chance to note Catherine's comment.
Yeah, I copied that into another box.
Great. Okay. If nothing else, I wanted to make sure you'll register.
Yeah.
That. But one thing I'll mention about the surveys and interviews. There's a fine line to walk in terms of what your anticipated findings are, without leading the witness, so to speak. If you know what I mean. You want to ask questions, but with a genuine curiosity, rather than setting it up to where you are funneling it toward a certain response. I don't suspect you're doing that, but I just want to point out there's a trick to there's a subtlety and a nuance to trying to set up interviews and surveys with an open mind that might lead you to something you never would have expected in terms of the responses. And so one way of thinking about that is when you offer multiple choices, you're already narrowing it down to the types of responses that can happen. At the same time, if you make long answers or short answers, you're less likely to get responses if you expect someone to type out a long answer. So I just want to point out to really be critical and careful about how you structure those surveys and interviews to allow a little bit of flexibility, but understanding that if it's complete open-ended thing, if you expect someone on the extreme end of the spectrum to just write you a paper and say, like, that'll never happen. So yeah, I would be mindful of that as you craft those.
Sure. Okay.
Let's see, just trying to catch up on those comments. And I think all of Catherine's comments are a good addition to a good overlay, a good addition to what we've been saying, and very, very helpful, as are Dason's additional comments he's added as well. Julie, I don't know if you have any comments before we transition to, before we move on to Young Lee's project.
No, I'm pretty familiar with Cole's work since we talk regularly. So great work, Cole. I'm excited to see where this goes.
Yeah, thanks, Cole. And Cole, I also appreciate the conciseness of your presentation to allow us to be able to absorb it and have this discussion after and not to allow each of the reviewers to actually think about this and to be able to provide some feedback and comment. And again, I think that your topic is very relevant to the point where it makes it very challenging for the reasons you described to capture data, because this is a socially relevant current thing, and even as you say, a touchy thing to do with retailers. So it's a relevant issue and topic, and I think there's plenty there to chew on, no pun intended. So I think we'll leave it there for Cole, and Young Lee, when you're ready, you can go ahead and share screen. So thanks, Cole. I look forward to seeing the progress on this in the coming semester.
Sure. Thank you, everyone.
I will add an editorial comment as we're transitioning over to Young Lee's project, that Young Lee is joining us from Korea. And so it's, is it 5:35 or 6:35 a.m., Young Lee?
Oh, it's 6:30.
6:30 a.m.
Yeah.
Good morning.
Yeah, exactly. A happy Thursday. Thanks. Just letting all the reviewers know, part of the reason we had some challenge to align these different reviews was trying to set this review at a time within regular business hours, roughly American Central Time, that was close to business hours. But because we're 14 hours apart, it was really a challenge. And so it's a little bit of compromise on both sides, right? Where it's at the end of the workday here, and even just before the beginning of the workday in Korea. So I wanted to acknowledge that partnership and appreciate the reviewers being here, and appreciate you being ready to present and having been online since before 5 a.m. your time. So thank you, Young Lee. And I'll let you go ahead and start your presentation when you're ready.
Okay. Hello, my name is Young Lee, and I'm going to present my thesis, energy efficiency analysis of climate responsible materials, mainly about dynamic breeding walls for the temporary shelters. This thesis is divided into two parts. I'm going to present today is the thesis A part, and thesis B will proceed this summer. Thesis A consists of three big categories. First is an analysis of biomimicry, and we'll explain why I choose thermoregulation and homeostasis in human bodies as a topic. The second is establishing a breeding wall design and its logical framework. It was started from the analysis of several smart materials for building envelope. The last part is the prototype house plan for temporary shelters. It is a practical approach for the actual house with a newly designed breeding wall. I will explain this is B part at the end of my presentation. Well, before I start to explain my thesis contents, I would like to share my research question. It was, can building envelope be equipped with thermoregulated materials like a living thing? So I started with the human or warm-blooded animal to analyze their thermal system. Biomimicry is a process of using nature expertise to solve human-made problems. Biomimicry is broadly used by imitating nature in its form, system, or process. Zenin Benyus, who is a co-founder of the Biomimicry Institute, discussed the three levels of mimicry approaches, which was organic level, behavioral level, and the last is ecosystem level. So this thesis aimed to pursue the ecosystem level of mimicry and find the sustainability and energy saving answer from the ecosystem. I thought about how human or animal can stand the extreme temperature. Because the building spends so much heating and cooling energy for human comfort, not because of survival. So, however, how the polar bear can survive from the Arctic with extreme freeze temperature, it was because of the thermal regulation system in warm blood animals. Thermal regulation is a process that allows the organism to maintain internal temperature, even the surrounding temperature goes up and down. Homeostasis is a tendency to maintain body temperature, a relatively constant internal environment. Like I say, homeostasis is a tendency to stabilize the internal temperature. So I researched the homeostasis mechanism in the human body. It is a breathing action. The physiological respiratory process is divided into two separate activities. The first is external respiration, which is called breathing. The breathing involves bringing air into the lung and releasing it externally. In this process, the diaphragm is an important structure to make physically move. Internal respiration is related to human homeostasis by gas exchanging in alveoli. Alveoli. Alveoli is an air pocket-shaped hole in the lung to exchange CO2 and O2. There is an ATP molecule in our body, and it transfers energy in cells. Because of this relation, when we breathe fast, it will spend more ATP and bring more gas exchange, and finally get more heat in the process. I found two interesting case studies, and I'll play on video. This project is breathing skin by Tobias Becker. He designed with an air pocket component on the wall with a thin binding volume like air pockets in between two layers wall. And those ends connected to two small holes on the wall. This breathe skin can regulate air volumes. This wall isn't using any mechanical devices, so it is passive method design strategy. This is an adaptable pneumatic skin project in Catalonia Institute. As you can see, this project is using a light sensor and air compressor to make the facade inflated or deflated. When the light sensor detects a high solar radiation, the balloon is inflated to expand it for creating shades. I could say this project is an active method design strategy compared to the previous cases. In this smart material analysis part, I was researching what facade strategy or material can stimulate or mimic the thermal regulation system. I had some difficulty choosing sustainable material terms in architecture because there are so many different terminology like adaptable materials, climate responsible material, intelligent facade, smart material, etc. The definition of smart material is an embedded technological function that involves specific environmental responses. I categorize that intelligent facade belongs to the smart materials categories. So the intelligent facade is incorporating technologies to provide indoor comfort and energy saving. The three parameters to be responsible are the weather, tech context, and occupied conditions. Example of intelligent facade are like double skin, or perforated wall, or corridor facade, or etc. Climate adaptable building shells are generally used to control radiate heat and filtrate natural light by shading device. Also, it can regulate natural ventilation and able to energy saving by responding from the external environment. A vertical greenery system also have the potential to improve thermal performance. According to the research, a vertical greenery system reduced the electric consumption by about 15% during the summertime. This was quite an effective method to reduce air conditioning use in the summertime. Also, biophilic design improve human well-being and psychological comfort to the occupants. Phase change material is a substance that can absorb heat and release it through a changing its physical state. PCM can store energy when the energy is surplus and release energy when it is energy deficit. The heat energy stores both latent and sensible heat. PCM can massive latent heat to use effectively, but without a refrigerator system, it cannot be used in normal conditions. So if I want to use store thermal energy, the sensible heat can be absorbed without any other electric thermal device. And only organic compounds such as paraffin and fatty acid can be used for a sensible heat store. A thermal biometer is laminated with different two materials which has different thermal coefficient. When the temperature rises, one side of metal will expand more than the other side. So this biometal is curved or curved by reacting outdoor temperature. It could be applied for various architectural use. For example, it can be used for shading structure to control object sunlight, or using for the self-detectable from the fire. One of the significant points is that this material can transform its shape without requiring an external sources. Breeding will increase energy efficient and improve indoor quality technology to draw a steady airflow through the wall and provide preheated ventilation and clean air. In the previous study, the energy efficiency of breeding walls can reduce 10 to 40% of heating and cooling load while providing filtrated air by HEPA standard. Breeding walls are incorporated with a dynamic insulation technique because it also uses airflow and thermal change in the walls through the cross and air permeable layers. Through the analysis of listed smart materials, I created a conclusion chart to understand which material technique have potential to design for thermal regulated wall. I found some strong points in PCM and breeding wall and energy flow and thermal response ponder aspect. According to a material literature review, the newly designed wall should meet this framework structure. Objective of wall should improve in both energy efficiency and indoor comfort, and reduced construction cost. The wall technique strategy should include dynamic insulation, breathing action in the wall, and heat exchanging techniques. So the wall will have double layered for active insulation. It will take a connecting loop for breathing action, and will use PCM for heating exchanging. This is a prototype of dynamic breathing wall design. On the sectional drawing, the inside air pocket moves by pneumatic pressure. When the inside air pocket is inflated, outside air flows into the inside, and vice versa. When inside air pocket deflated, outdoor air is not getting into the indoor. On the plan view, the dark color are the location of a PCM material, and it will be encapsulated. So when air travel inside the air pocket, the air will pass through the contacting the PCM material. I presume the outdoor air temperature will change because of the different temperature in PCM material. I plan to adopt this dynamic breathing wall to the temporary shelter. The first reason for selecting temporary shelter is this kind of type house is concerning only instantly constructed for non-permanent use rather than the energy efficiency aspect. The provisional temporary shelter is designed to be located in Austin, in Texas. It has 1 bedroom, 1 bathroom, 1 kitchen, and 1 living room size. And the gross area is 288 square feet. And the ceiling height will be 10 feet high. For the next Thesis B steps, I will make a small prototype model and experiment with how it kinetically moves and energy efficiency tests of this work. Thank you.
Thanks, Young Lee. Could you go back 1 slide to show that agenda? Thesis A. Yeah, there we go. No, to the one where you showed Thesis B and had your list of goals. No, to the second last slide, the very second last. Well, as you're pulling that up, yeah. Well, I will. You had mentioned on that slide creating a prototype, and I just wanted to clarify: are we talking about a virtual prototype or a physical prototype? What are you imagining in terms of that prototype, and how exactly how are you testing it?
Well, I'm thinking to simulate for energy consumption with this side of house, like using Open Studio tools.
Before you get to a prototype, I would suggest that you go back to the beginning. First of all, you're defining breathable walls in relationship to energy efficiency. And I think you have to be very clear about energy efficiency or interior air quality, whether it's about health or about energy. And I would suggest that you define, why does ASHRAE recommend 60 CFM per person for fresh air in a building? I would also recommend that you look at the history of how the number of air changes per hour has evolved in buildings. and the recommendations for those air changes per hour. I would also recommend that you look at our current process of breathable walls. That is, what is the nature of a vapor barrier? What is the nature of a vapor retarder? And so if you understand those elements, I think you jumped ahead a little bit where you got into smart materials, where you were talking about adaptable or responsive materials that right now are primarily based on shading devices as opposed to breathable walls. I understand you're trying to adopt some of their technology to make the walls more breathable, but I think our current technology using retarders to allow walls to breathe in at least our climate as opposed to vapor barriers, which are moisture barriers in other climates. And then I would say you need to begin to make a discussion about what is the advantage of a breathable wall over having an energy recovery ventilator, which ensures a certain amount of fresh air with heat recovery. I think those are the areas that really focus around breathing. And so is it breathable walls? Is it smart materials? I'm not sure that you can get into this prototype without more clearly defining what are the parameters and what is a discussion about breathable walls.
Yeah, I think those are really good. Sorry, were you going to say something, young lady?
No.
I think those are all really good points, Michael. And just to add a couple more in that vein, it's also not uncommon to separate the notion of the vapor retarder from the air barrier layer. And so those are two separate functions. They can be, one material or multiple different materials, but those are both, important considerations to think about here in terms of standard practice. And what you're proposing is something that deviates from that kind of standard practice pretty significantly. Definitely a lot of really interesting propositions there. I mean, it sounds like, what you're talking about, the two main kind of thermodynamic functions of this wall would be a heat storage function and a filtration function, which are also very different things. I think it'd be really important to have at least a really clear hypothesis about exactly what physical principles are being engaged here and how they're going to work. And it's not clear to me how it's going to have the effect that you're hoping for. Just for example, with phase change materials, you can get some really remarkable results out of phase change materials because of their extraordinary ability to store heat. However, you often find that that in a free running building, which is I think what you're proposing here, that's only going to work for a short period of time for any given season. And then you'll eventually end up with all the material either in its solid or liquid state, at which point it just behaves like pretty much any other material, and it doesn't really achieve that that massive heat storage or heat release capability if it's not going through that phase change. And to achieve that, you've pretty much got to have an average temperature that surface is exposed to that is pretty close to the heat of fusion, the temperature of fusion of that phase change material. So you can kind of tune it to one condition. It'd be really hard to tune it to, an annual cycle. And then, I don't really understand how the filtration function would work in terms of, I could see, okay, you're you're making kind of a tortuous path for the air. You're probably going to get particles deposited out of there, but then does the wall fill up with those particles? You know, what happens, you know, a couple of years down the road? So there are a lot of like real, you know, basic kind of physical process questions about what's going to happen. So I agree with Michael. I think you need to you know, really hone in on both exactly what the problem you're trying to solve is, what the parameters, you know, what a successful solution would look like, and then a really clear hypothesis on what the physical performance that you're engaging here is. Then as far as how to test something, I don't think you're going to be able to get what you're looking for out of Energy Plus and Open Studio. It can look at, it can use phase change materials. You can run the finite difference solution. You can even consider moisture adsorption into materials. But to my knowledge, you can't move air through a solid surface in either one of those. So I don't think it's really going to let you simulate the actual performance of what you're envisioning here. I don't actually know what tool would. Maybe it exists. Might. There's a reasonable chance that Woofy might, but I think you're going to have to really, if after you go through that first step of really dialing in exactly what you're trying to achieve and how you expect to achieve it, you're probably going to need to do some research on the tools you could use to get a better sense of, you know, an experimental result.
Yeah, I agree with yeah, I know how to, it's harder to using the Open Studio to calculate energy consumption with this model because the U value is keep changing because of dynamic insulation effect. So my plan is I just want to make a simple model which is able to move and then get test for the temperature change in that simple model, I guess.
You mean
And
a
then,
physical model?
Yeah, I mean like a simple physical model, and then get some parameter or changing temperature result, and then get back to the energy simulation, and then add some different two type of U value, like inflated condition and deflated conditions.
Let me pose a question in another way. Like the breathing wall is, I mean, it's really cool. That's neat. It's a fascinating idea. But why would it be better to make this incredibly complex wall assembly when you could just have a vent that brings in, or an ERV that brings in HEPA filtered air, rather than, you know, creating this incredibly complex mechanism to bring it through the wall itself? What's the driving point of that?
What's the driving point
of the wall instead of a system, if it's just a filter system?
Because
what's the driving point of it happening through the whole wall plane as a surface switch? Yeah.
Because my point was I want to make some where can regulate temperature rather than the air ventilation. So my point was temperature. I mean, like, my point was homeostasis of the wall first, and ventilation is second point, I guess.
Well, maybe if you told us that the wall would work passively as opposed to the ERV, which would maybe require a fan, we could understand it that way. But I think testing the wall, I mean, let's just accept that all you want to do is test the wall to see if a wall can be breathable, just to see how a different way to make a wall breathable. And, you know, in that case, I think you could probably set up a physical model and test it. You might also test the wall using CFD software, which would be about the only way I think you could do it.
Why is the CFD?
Martin, did you ask a question?
Oh yeah, I have a question. What is the CFD software?
Well, it's computerized fluid dynamic software, but it's how we're measuring airflow more accurately. Attila is an expert at this, and I would consult him. He teaches the course.
That's fundamental, because you know of those energy softwares will allow you to deal with pressure differentials. If Jason, correct me if I'm wrong, but I don't think those actually deal with pressure differentials, right? And if we're talking about, as Michael said, I think that I'm trying to wrap my head around it, but it seems to me that you are trying to come up with a system that is passive. Are you interested in the removal of the active, like, electricity-based system? Is that your ambition, or is your ambition, I don't know, a departure from the typical layered construction system in which certain issues are managed by different layers, and you're trying to kind of come up with like one system that would be doing all of that? If that's the case, then, you know, you might want to look at the work of someone like Sal Craig at McGill. He was at the GSD before. You know, he works on mainly bio-based, biogenic materials that are kind of heat exchangers. But one of his premises is the passive aspect, right? And the monomateric one layer construction system. So I think like some kind of a really clear premise for you of like, why do you need a new system? Is it an architectural desire, or is it a technical requirement? Is it a position that you want to take towards sustainability and the ways we do things? Is it about the impact of these materials beyond what this wall does on a daily basis? I think that those things are really important to clarify. So what Michael said at the very beginning, you know, it's before you decide to make a model, I think you need to do that, and also answer to yourself whether you think that you have already all the skills in terms of science and computation to actually be able to deal with such a complex issue, right? Because I think that without that kind of knowledge, you cannot prove whether your system does what you want it to do. And also the setup of a physical model is probably fundamental to the success of like understanding what kind of dynamics do you have to simulate? How are you going to set up even the space in which that happens? What's your, you know, what are the forces that need to be present? I don't know, this is, you know, I'm obviously not an expert here, but I think some basic questions need to be clarified.
First of all, I'm thinking to make a physical model with active method, so I can use some kind of like air compression or some device to physically move. So my biggest concept is the regulate temperature, and then the next thing is how the work kinetically move.
Okay, well, those are two different issues, right? Like one thing is how does this device mechanically work and can I make it work? The other thing is you mentioned the temperature differences. So you're talking about actually installing it in a very specific context to be able to test what's going on. And that requires an a setup of this I don't know, building a test prototype of your living unit, various issue of scale, right? Of all sorts of things that probably need to be addressed. So maybe you also want to make sure whether you're talking about testing just the mechanism of how it works or testing the effects of it.
Yeah, I think that's a general theme in a lot of the comments, Youngli, is just clarification. You have a lot of interesting things throughout a lot of things that you've explored and you're going to research and learn about different types of things. And so I think there's a lot here that you could run with, and it's a matter of clarifying the parameters and narrowing it down to being a very specific output, let's say. And I would say on top of that, which I don't think has been mentioned directly, is I wonder if it's just a distraction, if the temporary shelter itself, if that, and even just looking at this floor plan, just seeing this very specific singular application maybe limits a bit of the potential of what this could be if we were instead just talking about it as a surface itself, or that maybe could be, of course, enclosed as a volume. But I guess what I'm thinking is, of course, I'm tempted to have a discussion about the design of this shelter and what this could be, but I think that's beside the point. It's a distraction. It's not about, well, how might I lay this out? Unless you were to then say, well, perhaps we want a different environment for the living room and the kitchen and the bathroom and the bedroom, and perhaps we scale this wall breathes in different ways for each of those. But that's not what this is suggesting, and that maybe gets too nuanced. So I would just suggest that perhaps this particular application, the program that you've chosen, is maybe downplayed a fair amount. And or if you were even to do this, you might show here 3 different applications, because it's not about you designing the form of the object as much. It is about this breathable wall. It's about this. It's, as you say, the envelope. It's about the envelope and less about the actual program and function inside, but rather, anyway, I think I'm going in circles there a bit, but yeah. Julie, do you have any closing comment? I know that you're more familiar with this, obviously, but I don't know if you have any comments in conclusion there, or if Youngli, if maybe you want to stop share so we can see each other's faces all together.
Yeah, congratulations, Youngli, on some very extensive background research. I really liked that you looked at some of these older structures in South Korea and you got inspiration from those as well. I think what Michelle said earlier, or Dean Addington, about how to kind of create a framework for how to answer a question for someone later on is really helpful for master students to think about, because at the end of the day, you don't have as long as a PhD student has, so you should not pressure yourself necessarily to build a prototype or do physical testing. That can take a very long time, but just to go back as recommended and kind of think, how could you answer these questions, even if you don't rely on simulations, even if you don't have a prototype, a physical prototype? What other questions could you answer through case studies or, even design studies? And I also agree with, if you're getting into CFD or anything like this, to be in touch with Attila, as well as Dr. Nagy, as you already are, could be helpful.
All right. Well, I think we might conclude there. Thanks, Young Lee, for the presentation, and thanks to the viewers for all of your comments. And look forward to seeing the progress on this, Young Lee. I know that, and again, I also appreciate you joining us at an off hour, due to the time difference. But I look forward to you returning, hopefully in person in the fall. And I suppose we can all sign off here. So yeah, I see Ben and Maite's cameras are come back on. So yeah, congrats to all of you, to Ben, Maite, Cole, and Young Lee. And all the best for everyone. And we can go ahead and conclude.
Thank you.
Congratulations.
Yeah, nice work, everybody.
Thank you, reviewers.
Thank you, reviewers.
Thank you.